Welcome to this video. So this is a video I've made fairly in an impromptu style, but to try to get a playlist on special relativity started. Now, special relativity is the science that concerns how space and time are unified in order to preserve the idea that the speed of light as light moves through empty space or a vacuum is the same for all, at least non-accelerated observers relative to that light beam. Now this might sound a rather boring fact, but it is this idea and consequently the limits this imposes on how information can travel, and therefore what events can influence you in the future or could have influenced you in the past, as well as what kind of events can be considered to occur simultaneously and by whom, which leads to some very strange features of the universe, including, for example, even such seemingly unconnected things as the natural state of matter of mercury at room temperature. As we'll see in this playlist in some future video, mercury is a liquid due to a couple of reasons. One, much more quantum mechanical, to do with mercury in its ground state having electrons very far off in the what are called 6s orbital. But there's another component to it which is very significant, and that component is that due to relativity, and as we will see, due to, after a long line of reasoning, the idea of the speed of light being the same for all observers, one ends up concluding correctly that the electrons in a mercury atom have a lot more effective mass than their normal rest mass. So the electrons behave as if they're a lot heavier than when they would, say, be relatively stationary or moving at small velocities. And it's this which actually causes the size of the mercury atom to be substantially smaller than what one might think it would be classically, and thus mercury is really bad at letting go completely of electrons, and so prefers to share electrons, and thus bonds like elements or compounds which form liquids at room temperature. Mercury is essentially really bad at metallic bonding, partially thanks to relativity, and we'll look at that. So in this video, we're going to be introducing the broad timeline of special relativity and also the observational evidence for it, so that when we come on to the topics in later videos, you'll both know what kind of topics we'll look at, but also have a broad sense for the order of events which are led to the theory we will be discussing, although I will try to include as much historical content as possible in these slides as well, not to detract from the science, but to show how the ideas in special relativity evolved. So now we're going to move quite swiftly on. This will hopefully be a fairly short video. Most of my videos are over half an hour long, so I'm really trying to make a short one today, particularly as this is just an introduction video. But the story of relativity really began with the ideas in electromagnetism. So electromagnetism is the study of how changing electric fields, such as moving currents in a wire, can produce magnetic fields. And you can see this if you have a wire next to a compass and you turn on current in the wire, suddenly the needle in the compass will flip thanks to the produced magnetic field. But also the other half of electromagnetism is how changing magnetic fields can produce electric fields. And we see this in transformers, which are responsible for decreasing the voltage of electricity so it's safe to use once it has been transported to your house through the national grid. But also there are the transformers which are responsible for increasing the voltage to allow current to be to travel long distances, and thus allowing current to efficiently reach all the houses it needs to with very little energy loss. So transformers work due to electromagnetism using the idea of, well, actually they use both the idea that an alternating current will produce an alternating magnetic field, but also an alternating magnetic field will in the other coil of the transformer produce a new alternating current. And the advantage of transformers is they produce this new current through essentially the production of a alternating magnetic field which travels freely in space, meaning there's no kind of electrical energy in terms of electrical current going from one coiling transformer to the other, making transformers pretty much almost perfectly efficient. They're one of the most efficient, at least industrial devices, probably of modern humankind. So electromagnetism is both very common in nature and also hugely useful. But originally it was understood as a bunch of separate laws, and Maxwell combined these laws together. Now today we call these laws Maxwell's equations, and we've actually simplified the maths he wrote substantially. And we can do this nowadays because we have already in existence the maths to do it. We have vector calculus. But in Maxwell's day, he had to write the equations for the components of the electric and magnetic fields independently. So he couldn't write an equation for the whole electric field, say, or the whole magnetic field. He had to give an equation for each component of these fields. Meaning he ended up eventually with 20 simultaneous equations, and these were his Maxwell's equations. So it's not a surprise that they took some while to kind of gain traction in physics, partially due to how mathematically bulky they were, well, just really the fact of having 20 simultaneous equations. You know, those of you who have done simultaneous equations before will know that 2 simultaneous equations is fairly easy. 3 simultaneous equations, nowadays we will probably start using matrices, a fairly abstract bit of maths, but we would use it because already 3 simultaneous equations is a lot harder to solve than 2. If you have 4 simultaneous equations, you definitely want to use a matrix. And you could do it with 20, but the matrix you would have to solve the 20 simultaneous equations would be huge. And nowadays that wouldn't be a problem because computers can handle that easily, but if you're doing this by hand, this is really difficult. The other reason why Maxwell's equations didn't really stick on, initially anyway, is that whilst in 1864, Maxwell kind of encouraged the idea that his electromagnetic waves, which is how changing electric and magnetic fields travel, for example, travel really from one coil in the transformer to the other, um, are, are kind of moving in something called the ether. Now, the ether hadn't been observed. Indeed, today, the vast majority of physicists don't believe the ether exists, although there is still a tiny debate because, it's very hard to prove concretely nothing in all ways. Well, to prove completely that something in all ways definitely doesn't exist. But we've pretty much ruled out the idea of the ether now, although there is still some debate, and it's having something of a resurgence in the, more, I would say extreme, but more radical interpretations of physics. But, the ether not being observed was a drawback. And then in 1865, Maxwell wrote a document where he published his equations without reference to, well, any medium for the electromagnetic wave to travel on. And this was a big problem, such that at the time people thought his equations were seemingly incomplete, because the idea of a wave of any kind travelling, but being able to travel without a medium to travel upon, seemed just absurd. For example, if you have a water wave, well, it has to travel on a body of water. You can't have a water wave moving if there's no water molecules for the wave to move on. So, with Maxwell's equations with oscillating electric and magnetic fields, well, you could say, okay, well, it can happen because the fields themselves are oscillating, so the wave is sort of on the fields. But you can ask, well, yeah, but how do the fields travel? Because the fields aren't made of physical matter. They're more of a mathematical invention of the human mind. So, his work wasn't immediately, totally embraced, but eventually it was, mainly thanks to observational evidence that his predictions of the properties of electromagnetic waves actually reflected real electromagnetic waves, which turned out to be visible light and other parts of the electromagnetic spectrum, or what we would now call the electromagnetic spectrum. And the strange thing about his equations was that they predicted that if you have, let's say, light, or it could be, as I say, other parts of the electromagnetic spectrum, but let's say visible light, and visible light is moving through empty space. So, let's say, to a very good approximation, at least, light is moving through, the air, which is such small density that, to a good approximation, the light's travelling, almost in a vacuum, because the light barely interact with any air molecules, at least under, standard conditions, so, room pressure and temperature. Well, any two observers, providing the observers aren't accelerating relative to the light beam, will see the light beam moving at the same velocity, no matter the velocity of the observers. And what that meant was that the rules for how we classically add velocities, so the idea of what is called Galilean relativity, which describes traditionally how one adds velocity together, in terms of thinking of velocities as kind of vectors living in Euclidean space, kind of fell apart. And this led, and the kind of reconstruction of how geometry actually works in the universe, to the ideas in special relativity, which were kind of like shared with the world, really in 1905. So special relativity really solved the problem of light seemingly having a constant velocity for all observers by essentially talking about how time and space can be different or differently perceived for different observers, and how this can resolve certain paradoxes, and the way time and space therefore become entangled to account for the constancy of the speed of light leads to the idea of space-time. And Minkowski and Lorentz was greatly involved in discussing the geometry of vectors that live in this space-time, which today are called four vectors. Then, in 1907, so shortly after really publishing Special Relativity, Einstein wished to generalize it, because special relativity, it can talk about uniform acceleration. Often it's said that special relativity can't talk about acceleration at all, and that's simply false. Special relativity, although generally not used to talk about uniform acceleration, can do that. But a much more general form of relativity called, as the fairly uninspired name might suggest, general relativity, can take into account non-uniform acceleration. And in 1907, it was suggested to Einstein essentially realized that a search for a general form of relativity was equivalent to another thing he was trying to do, which was to describe the gravitational force and get a better understanding for, say, for example, where Newton's equation for gravity comes from, and why, say, objects with less mass produce gravitational fields. And then in 1913, Einstein was encouraged in a search to generalize his earlier theory of special relativity to look into a branch of geometry, a branch of non-Euclidean geometry, called Riemannian geometry, because Riemannian geometry allowed for, or really I should say pseudo-Riemannian geometry, allowed for the kinds of spaces, and particularly rules for how to calculate distance in such spaces, with these rules essentially being called metrics, that Einstein needed to talk about non-uniform acceleration in the context of space-time, as non-uniform acceleration in the context of space-time can be thought of as equivalent to an intrinsically curved space-time. Now you might think, okay, this means non-uniform acceleration causes space-time to be curved, but that's not really true. It's you represent non-uniform acceleration as the curvature of a mathematical object called space-time. Now, whether there is such a physical thing literally existing outside of the human mind as space-time, which can literally become curved, thus allowing gravity, is a matter of metaphysics, which brings us, or will bring us, to a brief mention about the philosophy of relativity. But it's worth saying, to believe in relativity, you don't have to believe that space-time actually exists externally to the human mind. You can just consider space-time and also its curvature a construction to allow us to describe the laws of physics. or if you like, a generalization of special relativity. And so, having now both the insight that non-uniform acceleration and gravity are kind of the same thing, and also that this thing would be well described using ideas of curvature discussed in Riemannian geometry, Einstein in 1915 published his theory of general relativity, filled with his field equations, although it's worth saying the solutions to these equations that Einstein gave were solutions based on his approximate techniques. He didn't have a way of solving his equations exactly. Indeed, solving them exactly in a direct way without, say, reference to some more broad ideas in physics, I'm not sure if even today is possible. Einstein, in fact, believed that no one would ever solve his equations exactly, due to their non-linear form, and also the fact that although we can write the equations very compactly, because the equations refer to curvature of space-time, which takes account of many combinations of bits of the metric of curved space-time, that there's a huge number of actual terms hidden in Einstein's equations, which would make, on the face of it, solving his equations very daunting, at least without approximate techniques. However, in 1916, only a year after general relativity was published, Karl Schwarzschild found the first non-trivial exact solution to Einstein's equations. When I say non-trivial, I mean, for example, thinking of things, say, more complicated than an empty space, which one knew would have to turn into have to be the flat Minkowski space-time special relativity. But in terms of predicting a genuinely new result in an exact form from general relativity, Karl Schwarzschild was the first one to get to that. And his equations describe the curved space-time around spherical masses, with a uniform matter density, providing those masses are not rotating. Now, in the real world, astronomical bodies, although generally spherical, are rotating, but often they're rotating slowly enough that his solution, the Schwarzschild metric, is a good enough description of the curved space-time around, spherical bodies, such as the Sun, and also, if you take Schwarzschild metric to the extreme, you end up predicting non-rotating black holes. Now, again, black holes rotate, but you can get a lot of aspects of black holes by just, considering their their properties if they wouldn't rotate. And it's worth saying that whilst nowadays, physicists are very confident that black holes exist, at the time the Schwarzschild metric was supposed, black holes were just a very cool and a wacky theoretical extension, an extreme kind of edge, if you like, on the mathematical landscape of the Schwarzschild metric. It wasn't clear that black holes actually existed in the universe, and it took a bit more theoretical probing, for example, if a star begins to collapse, considering, well, would the thermal energy prevent a black hole ever end up actually forming? And such matters like that, as well as a huge amount of observational data to start convincing the world that black holes truly did exist. But also in 1916, people tried to generalize the Schwarzschild metric, and some of this work eventually led to descriptions of, theoretical electrically charged black holes. I say theoretical because, we have no reason to suppose any real, at least macroscopic black hole in the universe would actually have a significant charge, but if they did, they would be described, we think, by the Reisner-Nordstrom metric or solution. Worth saying, there was a time when Einstein suggested that particles might actually be black holes, so this metric might indeed end up describing, say, charged particles like electrons, although if that's the case, there's still a lot of work to be done. And then in 1917, so you could see things happen very quickly after 1915. 1915, General Relativity published. 1960, exact solutions, beginnings of generalizations of the exact solutions. And in 1917, possibly, encouraged heavily by the work of Karl Schwarzschild, in seeing the power of his equations, although I don't know for certain, but I suspect that may have been partially a motivating factor. Einstein attempted to use his equations, which are called the field equations, to describe the evolution of the universe and to make his model consistent with kind of mainstream views on how the universe should evolve. He introduced a cosmological constant, although today we kind of keep this constant in, but for different purposes. We keep it in because this constant describes the consequences of a mysterious thing called dark energy, which, if it exists, is causing the acceleration of the universe, as in the expansion of the universe to be increasing in rate, not diminishing in rate. We're saying we might just not understand gravity, but assuming we do understand gravity, we need this cosmological constant to describe something called dark energy, which is having this bizarre kind of effect on the universe. So before we journey into looking at some of the observational evidence, or what today we consider to be observational evidence of special relativity, because at least this playlist will focus on special relativity, and if it goes very well, I might make one on general relativity too at some point. But before we go there, it's worth talking a little bit about the philosophy of relativity to avoid some possible confusion before in later videos we'll get on to the nitty-gritty of the theory. So one thing to note is that often texts that say books, particularly books for undergraduates, and even some popular science books as well, discuss relativity using terms and phrases that are very mysterious. Things like saying time and space are relative rather than absolute. And this can make relativity sound essentially like some strange form of mysticism. For example, if time and space are relative, and by that we mean in some fuzzy sense, they can be different in different reference frames, then the natural question is, can we pick a reference frame in which time and space are absolute? And if time and space are, shall I say, in a global or general sense relative, then what are they relative to? And these questions may sound odd, but they come from the very vague statements often made in literature about the content of relativity. Now, as I said before, relativity talks about how time and space are entangled with each other. But when I say that, it's worth saying when I'm talking about time, I am speaking of how long it takes to receive pieces of information. And when I'm talking about space, I'm talking about how far it appears, based on some rules for time that we, to a degree, invent, how far the information has to go once we've determined the velocity of the information we are sending out or receiving. So relativity is ultimately about the physics that comes from considering information transfer and the idea of there being, as we will see, a maximum speed at which information can transfer, which happens to be the speed of light. Well, is the speed of light, as we shall see almost by definition, in where the light travels through a vacuum anyway. So really, time and space are about information and making measurements of the external universe, assuming these measurements are made by perfect instruments. So we are not talking necessarily about some external structure to the observer in terms of dimensions of time and space as existing independently from concepts like measurement. Therefore, we're not necessarily talking about the properties of some exterior dimensions of time and space. And this is particularly important when we start to come on to thinking of, things like, for example, Lorentz transformations, which describe, how space-time appears differently if you change your velocity. It's important to consider that whilst we'll be using language such as, the kind of like one's axis in space-time rotating with some hyperbolic angle, and we'll be using terms like that, we don't literally necessarily mean that there is some structure external to the observer that has independent existence called space-time, whose axis literally start to rotate. Similarly, when we talk about general relativity, we will not be trying to when we say that space-time in to do with gravity has intrinsic curvature, when the space-time is resulting in the apparent appearance of a gravitational force, we don't necessarily mean that there is some external structure called space-time to the observer which has independent existence of the observer and is literally intrinsically curved. We're not talking When we say about space-time, we're talking ultimately about measurements made by an observer, and we're considering how to compare measurements different observers would make using a mathematical structure of space-time. It's a mathematical abstraction. Now, space-time may literally exist external to an observer. It may have some independent meaning. However, the discussion of that, whilst definitely something worth looking into, I don't mean, as a lot of physicists seem to sometimes do, to bash questions such as talking about, well, is space-time, if you like, literally real? I think such questions are very important, but they fall under a category of philosophy called metaphysics, a branch of physics really that Aristotle was hugely helpful in kind of, really laying the foundations for. I mean, Aristotle did a great many things, including also, laying the foundation for formal logic, which also is helpful to mathematicians. Well, formal logic is a benefit to mathematicians too. It's not just a philosophical thing. But whilst metaphysics is fascinating, and I would encourage everyone to, look a little into it, in physics, since physics is a science, we are concerned ultimately there with experiments which are to do with what observers would measure, much less than we are concerned about external realities apart from the observer. Just a comment worth making. So if I, use strange and mysterious words that imply that space-time has some, external reality apart from an observer, that is just, I suppose a degree of poetic license that many textbooks enjoy, but it is worth pointing out the subtlety on the philosophy of relativity before we, look at detail at the maths and forget a little bit, perhaps, the philosophy in oncoming slides. So now, having talked a little bit about the philosophy of special relativity, time to get on to some pardon me, time to get on to some novel applications. So the first one is a phenomenon called neutrino oscillation, which we can see a graph of there. Now I'll explain what the graph is showing after I talk a little bit about what neutrino oscillation is. And really where the nuclear comes from. So the nuclear comes from when scientists were trying to understand nuclear processes occurring in the sun. At that time, it was known that the sun produces energy through fusion, which is another novel application of special relativity I'll come on to in a couple of examples' time. But we knew enough to know that the sun produced energy through fusion. We also knew enough to know that nuclear fusion would involve particles called neutrinos to be emitted from the sun's core. Now, neutrinos are like partner particles to electrons and heavier version of electrons called, the electrons and, its heavier cousins, if you like, are collectively, like one half of a group of particles called leptons, and the other half of the leptons is these neutrinos. So each neutrino has an associated, charged particle. So the electron has the electron neutrino, the muon has the muon neutrino, and the tauon has the tau neutrino. Now, detecting electrons and its heavier cousins, the muon and tauon, is not too difficult because these particles are charged principally, so they interact through the electromagnetic force, And also, although the electrons quite light, the muon and tauon do have significant mass. However, neutrinos are far more evasive because neutrinos have incredibly little mass. In fact, the upper bound of the mass of a neutrino makes the rest mass of an electron seem huge. That's how light neutrinos are. Neutrinos also don't have any charge. They're neutral, so they don't interact via the electromagnetic force at all. And also, since neutrinos are leptons, they don't interact with forces that hold quarks together. So they don't feel, unlike the proton and the neutron, the strong nuclear force. So because of that, essentially 3 out of the 4 fundamental forces, the gravitational force, the electromagnetic force, and the strong nuclear force, the neutrinos barely feel, or with some don't, or with some of these forces don't feel at all. The only way neutrinos can really be detected, therefore, is based on how they interact with their associated lepton through the weak interaction. But due to the weak interaction, the electron neutrino, for example, will be able to interact with an electron. However, it won't be able to interact, or we say using quantum field theory language, the electron neutrino won't be able to couple to the muon or the tauon. Therefore, when we're detecting a neutrino, we're detecting a particular type of neutrino, which our instrument will be sensitive to, and we won't generally be able to detect the others using that instrument. And we call the type of the neutrino, say the electron neutrino or the muon neutrino or the tau neutrino, we call the type the flavour. I don't know why we use that term. We're not going to eat these fundamental particles for breakfast, but for some reason we use the term flavour to refer to the type of, in this case, neutrino we're dealing with. So we looked at what of a particular type. I think it was the electron neutrino, I could be wrong. Of a particular type of neutrino that the sun was emitting. And we had our detectors already on Earth, and we seem to observe far less of this neutrino, this type of neutrino, than we had theoretically predicted. And so theorists were like, well, there must be something wrong with the apparatus, and the experimentalists were like, no, there's nothing wrong with the apparatus. Your models for just nuclear processes in the sun is just wrong. The sun is actually genuinely producing far less neutrinos than your models suggest it should. The actual solution to this was neither fixing the theory nor the experiment, because both were working fine. The solution was adding in a new detail to the theory, so not changing the amount of neutrinos predicted has been created, but introducing the idea of neutrino oscillation. The idea that the neutrinos having some kind of mass, if very tiny mass, are able to change their flavour, that is the type of neutrino they are, such that when we detect them, we detect as sensitive to only a particular type of neutrino. We detect less of that type than the number of that type of neutrino that the sun actually sent our way, because some of the initial neutrinos of that type have kind of, we say, oscillated into other flavours. And we could see on a graph here 3 curves referring to 3 flavours of the neutrino, and we can see that the probability of of finding a neutrino in a particular flavour. So, say the black line, I think, refers to the probability of finding the neutrino as an electron neutrino changes based on time, or in other words, based on, the length divided by the energy of the neutrino, because energy is another, if you like, measure of velocity. So when we're doing length over energy, in a sense, although in slightly different units, we're working out how long the neutrinos are travelling. And you can see as time progresses, the neutrino flavour seems to oscillate. That is, the probability of the neutrino having a particular flavour changes periodically. So that's neutrino oscillation, and neutrino oscillation, as I say, can happen because neutrinos have mass. And you might ask, well, how can mass allow a particle to change from one type of particle to another? Well, it's because mass actually refers to energy, and energy, as we know in quantum mechanics, is responsible for allowing the state of a system to evolve. But the crucial relationship between mass and energy, which links neutrinos having mass to neutrinos being able to oscillate, that link is E equals mc squared, the famous equation of special relativity that goes, well, because neutrinos have less mass, they have associated with that a particular type of energy. And when we come on to looking at applications of special relativity in terms of neutrino oscillation in more detail, we'll talk more about why particularly energy associated with mass causes neutrino oscillation. But neutrino oscillation is important if you want to know, say, the nuclear processes going on in stars, and therefore understand the life cycle of the stars, not just the sun, but stars in other points of their life cycle too. And neutrinos are really good to use to study these the processes going on in the core of these stars, because they are so weakly interacting and don't interact barely at all in terms of three of the fundamental forces. It means neutrinos can escape stars very easily. The challenge, however, is detecting them. So neutrinos are great for studying stars, but you need to take account of neutrino oscillation to actually recalibrate your results to understand the original population of a particular flavour of neutrinos that the star emitted, and thus use experiment correctly to infer whether your theoretical models of stellar evolution is right or not. Another fairly novel application of special relativity is mercury, or rather the state and matter of mercury. Now, there's actually a few reasons why mercury has some very unusual properties. But in terms of it being a liquid, which is very unusual for metals, it's really special relativity. So, to understand why it's a liquid, we have to consider liquids as almost being in between gases and solids. And so if we think about how gases and solids exist in the universe, well, say we have an element that is made up of atoms, and we're considering the state of the element at room temperature under standard conditions. Well, if the atoms, say, of the element are like atoms of a noble gas, for example, then the atoms are very good at holding on to their electrons. It's because the electron structure in a noble gas is very, very stable, so an atom doesn't really want to do anything with its electrons. So, because the electronic structure of things like, noble gas atoms is so stable, electrons can't really do anything interesting, and each atom just keeps the electrons to itself. And a similar thing can happen with kind of molecules, with very small molecules. And so because of that, compounds made of very small molecules like methane, oxygen, carbon dioxide, so on, as well as kind of noble gases are, well, gases under standard conditions. Solids are the other extreme. So in gases, the electrons in the atoms that make up the molecules, the electrons kind of in the gas associated with the atoms and molecules in the gas don't like doing anything interesting. They just hold tightly to the atom. Whereas in a solid, electrons can be gained or lost and freely kind of like, if you like, transferred. There are some rules about how many electrons can be transferred and where they have to be transferred from in terms of what electrons in the atom are transferred, but just generally, when it comes to a solid, atoms really want to get rid of or gain or in some way exchange electrons to be very stable, to end up being very stable. And this exchange of electrons then leads to very strong kind of electrostatic forces occurring in the solid, which keeps the kind of atoms very, very, very close together, and prevents thermal kind of excitations just pushing the atoms apart, meaning the compound ends up forming a solid, or the element is a kind of solid under standard conditions. Liquids are in between the two. Say we have a element made up of atoms. If the element is a liquid under standard conditions, then that means the atoms don't quite want to fully hold on to their electrons. So in other words, the element doesn't end up existing as a gas at room temperature. But equally, the atoms don't really want to start exchanging or getting rid of or receiving electrons completely. And so the element doesn't form a solid at room temperature. Instead, the electrons do something halfway. The electrons kind of stay to their, if you like, parent atom, but they are also kind of slightly allowed to wander to neighbouring atoms, and so we say the electrons are shared, and it's this sharing of electrons that allows the liquids to form. But mercury is a metal, so you might wonder, well, why is mercury, unlike all other metals in the periodic table, not a solid? Why is mercury a liquid? Well, it's because, thanks to relativity, mercury atoms want to share electrons. They don't, unlike atoms of many other metallic elements, want to kind of just get rid of outer electrons and just let these outer electrons wander freely from the parent atoms in the metallic lattice. And the reason why mercury atoms are very bad at letting electrons out, these outer electrons in the mercury atoms completely go, is because the pull from the nucleus of a mercury atom, due to the high charge density of mercury nuclei, is so strong that the electrons in a mercury atom are actually moving relativistically, and an effect of this is they move as if they have much more mass than they would do if, say, the electrons were moving much slower. And because the electrons in mercury atoms act as if they have a lot larger mass, it means that the mercury atom ends up being a lot smaller, because, if you like, it's a lot harder to just fling these electrons into larger orbits around the nucleus. And atom is so small, the electrons, even the outer electrons in the mercury atom, are really, really close to the nucleus and therefore very tightly bound. So mercury is terrible at letting these outer electrons go. Thus, mercury does not undergo metallic bonding, and mercury prefers rather to kind of share these outer electrons, and thus mercury is a liquid at room temperature. So, special relativity might sound like it's about time and space, but it's about very tangible things, very down-to-earth things, about, for example, the state of matter of mercury. So, it's far from, unrelated to very direct and tangible aspects of the world. And lastly, we consider the sun and fusion. So as I mentioned before, the sun kind of undergoes fusion in its core, and it's this process that produces energy. Now, how the sun produced energy before we knew about fusion was a big confusion. There were two main candidates for how the sun might produce energy before we really knew about fusion, and really before we knew about quantum mechanics or relativity at all. One of the suggestions was that the sun might be, because at this time, as I say, we didn't know much about quantum mechanics, so we couldn't really analyse, light spectra from the sun, so we didn't really know what the sun was made up of. So it seemed plausible that the sun might just be made up of hydrocarbons, like the hydrocarbons that make up fuels like gasoline, or the hydrocarbons you'll find in things like petrol. And, just as when these, fuels on Earth get hot, they ignite, the same thing might be happening with the sun. The sun might just literally be a burning ball of gas, albeit a very, very, very large one, a burning ball of hydrocarbons. And it might be producing energy through combustion. But because combustion is a very, very easy to do reaction on Earth, we could get very confident results on how much energy combustion can actually produce. And using Newton's law of gravity and other things, we can get a good idea for the mass of the sun, so we can go, well, given its mass, assuming it is made up entirely out of hydrocarbons, then given how much energy on average you get when you burn hydrocarbon fuel, how much energy could the sun potentially produce if it combusted all its hydrocarbons? And then once you have the total amount of energy the sun could produce, you can divide that by the current rate the sun is releasing energy. And from that you can get, well, how long could the sun be producing energy, or being producing energy for, if it was producing energy through burning hydrocarbons. However, it turned out that the sun wouldn't have been able to be producing energy through hydrocarbons, at the rate it's producing energy, and giving its mass for very long at all. In fact, if the sun produced energy through burning hydrocarbons, it would have to have started this process less than 1 million years ago, but through fossil records we know that life existed long before 1 million years ago, or even a few million years ago. We know life, which made use of the sun's energy, is billions of years old. I mean, even if we're talking kind of like, large scale multicellular organisms which are very complex, well, that kind of life itself is even older, even just a little bit, than 1 billion years old. So you know, the sun couldn't possibly be producing energy through burning hydrocarbons. Giving its mass and how much energy you get from burning hydrocarbons, the rate it emits energy, it just didn't add up. The next suggestion was that perhaps the sun is slowly contracting. And as it contracts, it exchanges gravitational potential energy for thermal energy, where the sun's interior heats up, and this thermal energy is kind of emitted as blackbody radiation, so mostly infrared but also visible light, to the Earth. And this is reasonably plausible. But again, if you consider the mass of the star, the mass of the sun, and how much energy it's producing, the sun would have had to start contracting not very long ago in order for it still to be around and still to have the capacity to therefore keep contracting in order to produce the energy to sustain life. And again, fossil records showed the sun was producing energy, much further back than than the model of, if you like, star contraction would allow. So we were at a loss for what was actually happening, but then relativity came along, and one consequence of looking at space-time and vectors in space-time called 4 vectors is a particular equation for energy, which ends up predicting that you can create energy, if you like, by getting rid of mass, because mass is a particular form of energy, so you can really just convert mass into energy. And the sun is doing this right now. It's losing mass and converting that mass directly into energy. And the process in which mass is lost is a process called nuclear fusion. It's partly thanks to quantum mechanics this process can happen at a high enough rate to allow the sun to produce so much energy so quickly. However, it is ultimately relativity, not quantum mechanics, that explains how nuclear fusion can produce energy through the loss of mass, or what physicists call a mass defect, at all. So these are 3 novel applications, I think fairly novel, of relativity: neutrino oscillation, the states of matter and mercury under standard conditions, and the production of energy in the sun. And in this course of videos I will try to keep the applications of relativity novel, because there are plenty of videos out there on more standard applications of relativity, like kind of time dilation with clocks and stuff. So I'll try to keep it novel, but I hope this video has been a good introduction to the playlist. I do apologise for the video being fairly long. I try to keep my videos short, but I'd never want to rush them, and there's so much content to discuss, and I want to give more than a just fuzzy, unsatisfactory overview. But I hope this video has encouraged you to, keep an eye on updates to this playlist if you'd like to learn relativity through YouTube. But also, if you prefer to learn relativity through kind of other media like books, there are many good books on relativity. Hopefully this video has been a good introduction to its many uses, and also a bit of the history and a touch of the philosophy of relativity. But now for this playlist, as we've got the intro now done and we've given the motivation and the context, we're going to, in the next video, start exploring much more technically and mathematically relativity, but we'll keep close to our hearts the physics and the observational evidence that makes relativity more than just an abstract concept, but crucial to the physical world around us as we experience it.